Hello, so I will be going through the 2009 Mechanics 2 FRQ, which encompasses rotation and simple harmonic motion. So first, let's begin with a little background on motion. There are two types, linear motion and rotational motion, as you can see on the left side in the chart. So linear motion occurs when a force is exerted on an object and causes it to move linearly or backwards and forwards, while rotational motion causes an object to spin in a curved path when torque is applied to the object. So the amount of torque required to make an object spin is what's called the object's rotational inertia, and it's affected by three things: the object's mass, shape, and mass distribution. It plays the same role as ordinary mass in linear motion, which gives us Newton's second law. As you can see in the picture in the bottom right, the force applied to an object causes it to move linearly, while the torque applied to an object causes it to move rotationally, which allows us to replace those when we convert between the different forms of motion. The mass of the mass in linear motion is the same as the inertia in angular motion, so those can be replaced as well. And since linear motion occurs just in a straight line, we only need the regular acceleration, while for angular motion, since we're moving in a curved path or at an angle, we need the angular acceleration. This applies to um, different functions as well if you look in the chart on the left, but the Newton's second law is the one that matters the most for this FRQ. So the location of application is another key aspect that we should cover. So because rotational inertia varies throughout an object, where you apply the torque is important. For example, if you apply torque at the center of mass, no rotation occurs at all. And so the picture in the top right gives a good idea of what this is referring to. So if you think about pushing a door, if you were to push near the hinge or on the hinge, there would be no rotation at all, as opposed to on the other side of the door, which is represented in part B. They um they state that there's plenty of torque when you apply the same force on the opposite side of the hinge, but when you apply it on the hinge, there is no torque at all. And so in addition to this, we also need to cover simple harmonic motion. Essentially, simple harmonic motion is periodic motion in which the restoring force is proportional to the displacement. The function oscillates continuously and has an equal displacement on both sides of the x-axis. And this is important in how springs work. As you can see in the bottom right picture, the ball is attached to the spring and it's pushed all the way up to its peak, released to extend all the way out and displace in um the exact same amount in the opposite direction, and then go back right to where the peak was originally before just continuing this oscillatory motion. And the bottom left picture shows essentially the same thing, except it labels the different aspects that are very important. For example, the amount of displacement is equal to the amplitude, and the period is essentially the time period between each peak. And the visual labeled bar in the top right provides an accurate depiction of what will occur in this FRQ problem. So let me start the animation right here. So as you can see, the bar is moving back and forth, allowing it to displace to the left a set amount of distance, and also displace that exact same amount of distance on the right side as well. So let's begin with the FRQ itself now. And I've gone ahead and dissected the prompt myself, although I want um I want to read it first and then explain what you guys should be looking for when you take an FRQ similar to this as well. So you're given a long, thin rectangular bar of known mass m and length L with a pivot attached to one end. The bar has a non-uniform mass density, and the center of mass is located a known distance x from the end with the pivot. You are to determine the rotational inertia IB of the bar about the pivot by suspending the bar from the pivot as shown above and allowing it to swing. Express all answers in terms of rotational inertia, or IB, the given quantities, and fundamental constants. So I went ahead and color coded my three key sets of information. So the first important info is the given quantities we were given. As it states at the very end of the prompt, we must express all our algebraic answers in terms of the rotational inertia, the fundamental constants, and the given quantities. In this case, the given quantities include that the bar that has a mass of m, a length of L, a rotational inertia of IB, and a center of mass that is located a known distance x from the end of the pivot. In addition to this, they've also given us some important information which will sort of tell us how to approach the problem as a whole. This includes that the bar has a non-uniform mass density, and that in part A1 we must use the appropriate equation of motion, which will sort of dictate the rest of the problem. And finally, there are the direction words, which include write, calculate, and describe in this problem. And these basically tell us what type of answer they're looking for. For example, in part A1, since we only write a differential equation, we're not doing anything but set it up, as opposed to part A2, where we're most likely going to be calculating something with that equation that we got from part A1. And in both B and C, we're given the term describe, which will most likely mean that we will be giving a qualitative answer about the experiment as a whole, as opposed to a quantitative answer like part A1 and more specifically A2. So in part A1, we are going to first read the prompt and notice any keywords which we described last time. So first, let's just begin by reading the prompt. By applying the appropriate equation of motion to the bar, write the differential equation for the angle theta the bar makes with the vertical. So in this case, since it says to use the appropriate equation of motion, and we know this involves rotational motion, we are going to use sigma torque equals rotational inertia times angular acceleration. And if you notice in the prompt, it stated that the bar is suspended and dropped to swing back and forth. So therefore, this means that the only torque applied is the gravitational torque. And this gravitational torque, after we substitute it for sigma torque, can be simplified into what it actually is defined as. So what torque is actually defined as involves a cross product. So instead of recognizing the cross product, I'm going to just tell you what the product of three things that it is. So it is the product of force, which in this case, there's only gravitational torque because the bar is suspended and dropped. Therefore, it is negative mg, and negative because we're going in the opposite direction. Then we multiply that by the distance from the point of rotation to where the force is applied. This was given in the problem as x as a given quantity, which is why we want to make sure we underline it. And then finally, we multiply both of those by the sine of the angle between the line we measure distance along and the line of the force. In this case, since we are using theta, it is going to be sine theta. So when we multiply these three things together, we could set it to the rotational inertia times the angular acceleration. And as you remember for linear motion, where we could convert a to x or acceleration to displacement/position by doing the double integral of acceleration, we could do the double integral of angular acceleration for angular position, and therefore angular acceleration can be represented as the double derivative of theta, or angular displacement or position. So next we're going to be looking at part B. But before we do so, let's quickly look at the rubric and see what we would have gotten points for. So first, the first point out of 4 on this problem would be given for using the correct form of Newton's second law. As I said, this involves rotational motion as opposed to linear motion. Therefore, sigma torque equals rotational inertia times A would give us 1 point, as opposed to sigma F equals ma. Then, since we know the torque is the product of the three things I mentioned before, we would get a point for listing all three of those and multiplying them together. Then, since, as I said, it is gravitational torque and acts in the opposite direction, we must put a negative sign at the front, which would give us the third point. And finally, for expressing the acceleration as the second derivative of position, or angular position, or theta, we would get the final point out of 4. So part 2 of A, by applying the small angle approximation to your differential equation, calculate the period of the bar's motion. So first, let's recall the small angle approximation, which essentially states that as we approach the origin from the right side of a sine function, so this way, the x and y values become closer and closer until we can basically call them equal at points very close to the origin. And using this, we could manipulate our differential equation to calculate the period. So first, I began by copying down the differential equation we got in part 1 of A initially and divided by inertia on both sides. Then I applied the small angle approximation, which allowed me to replace the sine theta for theta. And at this step, since everything was equal to the angular acceleration, we couldn't plug it into the period function, which is 2 pi over omega, because the omega represents angular velocity and we have angular acceleration. But if you look at the equation sheet, you'll see the equation x equals x max times the cosine of the quantity omega t plus phi. So I first replaced the position with angular position and the x max with a. Then after this, I began to differentiate this twice since this is angular position and we currently have angular acceleration, which left me with negative omega squared times a times the cosine of the quantity omega t plus phi. And as you might notice, a times the cosine of the quantity omega t plus phi is what theta equals, if you look back up here. So this allowed me to plug back theta into the equation and essentially have the angular acceleration as equal to negative omega squared times theta. So at this step, I decided to plug this in for the angular acceleration we had in our differential equation. And if you continue on solving, you could eliminate the negative theta, which is found on both sides, to be left with omega squared. And then after this, when you take the square root of both sides, you are left with omega, which can finally be plugged into the equation for period, giving us the equation that calculates the period of the bar's motion. So using this, we would get all 4 points because at the very beginning, we showed that we knew the small angle approximation by replacing the sine theta in our differential equation with theta. Then the second point was given for recognizing that the coefficient of theta is omega squared. And we got to this step after we had derived what angular acceleration was equal to and eliminated the negative theta on both sides. And after this is a very interesting point that you can receive. So this point is only given for showing the relationship between t and omega. So the equation itself is found on the equation sheet and requires no calculating, no writing, no nothing. It's just a simple equation you copy down, which can give you 1 out of 4 points. So make sure that when you're solving one of these problems, you always write down every single equation that could be necessary because you never know when you're going to get a point. And then finally, to get t, we plugged in omega, and that gave us the last point, which, as you can see, their equation is identical to ours. So now part B. Describe the experimental procedure you would use to make the additional measurements needed to determine IB. Include how you might use your measurements to obtain IB and how you would minimize the experimental error. So if you look at the original prompt, you'll see that it states that we have a known mass M, length L, and center of mass located x distance away from the end of the pivot. Since gravity is a constant, we're only left with 2 unknown variables if we were to use the equation we derived in part 2 of A. And these 2 variables are period and the inertia itself, IB. So using this information, we can begin designing the experiment. Since they want us to calculate IB, it would be much easier to solve for t and then plug that into our equation and get IB as opposed to the other way around. So in order to determine the rotational inertia of the bar, we must run an experiment that gives us the period and use that to solve for IB. To do so, we must first displace the bar slightly. As soon as the bar is released, we must then use a stopwatch to begin recording the time it takes for the bar to reach the maximum displacement in the opposite direction and return to the maximum displacement in the direction we started at. So this time can be substituted for t into the equation found below, which was derived in part 2 of A, and solved for IB. To minimize the experimental error, having the bar oscillate multiple times, then dividing it by the number of oscillations to find t can provide a more accurate period and thus a more accurate rotational inertia. So with this explanation, we would receive full credit. So the first point is given for a valid approach, and as you can see in example 1 over here, the prompt uses a very similar approach. The next 2 points are given for explaining how the variables will be measured or calculated and the equipment used. So our explanation, stated that we will measure t with a stopwatch and then use that to calculate the rotational inertia with the equation from part 2 of A. And then finally, the last point is given for stating how we could reduce the or minimize the error, and that was given to us when we stated that finding the average of a larger number of oscillations would give us a more accurate period, which would thus give us a more accurate rotational inertia. So finally, we have part C. Now suppose that you are not given the location of the center of mass of the bar. Describe an experimental procedure that you could use to determine it, including the equipment that you would need. So as we reviewed earlier, the center of mass is the point where all of the mass of the object is concentrated. When an object is supported at its center of mass, there is no net torque acting on it and acting on the body, and it will remain in static equilibrium. Because the center of mass is the point at which an object's entire mass is concentrated, the object can balance at this point. So in my experiment, I decided to use a table and push the bar off the edge slowly until it reached this point, this balancing point. And here is the experiment itself. So to find the center of mass, first begin by placing the bar on a level surface with an edge such as a table. After that, slowly begin pushing the bar off of the edge until it reaches a point where the bar can balance without tipping over. So for this part, we're only given 2 points, so it might be better to not spend a lot of time writing a lengthy response. As you can see, the first point is given for having a valid approach, and since our approach was similar to example 2's, we do get this point and have a valid procedure. And the other point is given for specifying the equipment used, which in this case was nothing more than a bar and a table. So I hope you guys enjoyed and learned something along the way. If you follow these steps, I'm sure you can get a 15 out of 15 just like we did together.